recording again to see what happens. It's still mad at me. Why is it mad at me? I'm not going to know, but I'm just going to have to go through and do the best I can. All right, here we go. So, I put up a new example. Yes, I also cannot leave well enough alone, and I am my worst enemy. So it took forever to get this right, so to speak, because even though I had this entire example from last time, I wanted to add functions to show how to compute things in both R and Stata, because I've gotten a lot better at that in the last however long. So I thought, rather than dip back into the slides from last week, that we could go over the same concepts in the context of a numeric example. How's that sound? Does that work for folks, or do we want to do a little bit of review first? I know it's Tuesday, it's a happy garbage day. We got to get our heads back into this space here. Any thoughts? Numbers first, review first?
I'm good with numbers.
Numbers?
I love numbers.
We love numbers, okay. Well, since we're enthusiastic, let's do this. So this is a new data set. The variables are going to sound awfully similar though, but this data set is real. That's why the data is not included in the example download folder. A version of this data set is included in the data example for the multi-level measurement modeling workshop that Jonathan and I taught, where we used 10 items out of a math test and fit a 2-level IRT model to them. This is using a total score for math test because this is not a measurement class, but that would be the righter way to do this. So we're going to be predicting math from 10th grade students in a Midwestern rectangular state. So this is an end of grade test. Yeah, take your pick as to which one that is. It's not exactly identifying information. I have one predictor. Okay, this handout is 23 pages long, and I have one predictor. It is whether the student pays full price for lunch as 0, whether they receive reduced price as a 1, and whether they receive free lunch as a 2, an ordinal student level predictor. So the reason that this one predictor is going to take up 23 pages is this one variable in here in terms of how it would represent student differences? Probably not. This is not a number, right? This is a category. So if I have 3 categories, how many slopes do I need at a minimum to represent those differences? I need 2. Okay, so my one predictor just turned into 2. Now, students are not randomly assigned to their schools. So if I have 2 predictors at level 1 to distinguish the students, how many do I need at level 2 to distinguish the schools? 2. Okay. This is also going to examine moderation. Does it suck more to be poor if the rest of your school is poor than if the rest of your school is not poor? So that is potentially multiple interaction terms and at multiple levels. So it's going to get a little ugly considering it's just one predictor, but it is a realistic example.
It reminds me of my math.
It kind of does, yeah. So we've got example 4 data reading in. I've got 3 variables in the data set. This actually should be a 3-level model with districts, but too bad. It's already not right in some regards, so it's not going to be right there either. So more concretely, what? I can't do everything all at once.
I'm joking.
Y'all would be completely overwhelmed, and you're already overwhelmed with everything else. So we got to pick it in pieces here. So more concretely, I have students who are nested in schools, and schools are nested in districts. If I just fit a 2-level model of students nested in schools, then what I am saying is that districts from the same school are uncorrelated. That's what a lack of a 3rd level would say. If I did a single level model, either a traditional IRT type analysis or a traditional regression type analysis, those are both single level models, then I would be assuming that students from the same school are uncorrelated. So these are all empirically testable assumptions. I don't know much information about the districts. I don't think there's too many of them in this case. And again, I'm ignoring it for today, but we can live with that. So here are the proportions of students who fit under each of these categories. Most of the students, about 70%, pay for their lunch. A smaller amount have reduced price lunch, and then there's free lunch. And so there's a sliding scale. If your family income is below this amount, you get reduced. If it's below this amount, you get free. So there's a table you can do it. So given this ordinal coding scale, and given that most of the time this variable is dichotomized into paid lunch versus free or reduced, like that's how people talk about this variable, free and reduced lunch, is like one idea, that's an empirical question. So we're going to start out with a model in which this is the sole representation of this variable. So I'm lumping together reduced and free as a sign of some kind of economic instability. However, I can further differentiate if there is a difference between reduced and free by then adding in this second column. And so this is not a traditional dummy-coded type setup. This one here turns it into something that I call sequential. That's a term that the regression text I use also uses. And so what this does is it differentiates paid versus reduced and free, but then once this gets into the model, this differentiates only paid and reduced. This steps in to further differentiate reduced and free. So it's an alternative coding scheme that's designed to give sequential differences between adjacent categories, which for ordinal data can sometimes be more useful. So that's my setup. I've got everything in R from below too, and I've got some output mixed in from SAS because it's prettier. So I've got everything and everything though. We've got then, in Stata first, I'm taking the original lunch variable and turning it into these two contrasts. So starting with blanks and then systematically recoding. If lunch is this, so equal equal is an equality sign, like it's checking to see if that's true. And then it's going to assign 0 if it is true for those. I am then, for demonstration purposes for school composition, essentially computing redundant information. So I am generating lunch indicator specific dummy codes to where if you're in the 0 group, you get a 1 for that and a 0 otherwise. Lunch 1, if you're in the reduced group, you get a 1 and 0 otherwise. And 2, if you're in the free group, you get a 1 and 0 otherwise. That way we can see at the school level how many students we have in each category on average. I'm filtering, actually, that should have been done. Nope, we're good, we're good. Filtering to make sure that everyone has math and lunch as the two variables in the analysis. Then we're computing cluster means as well as the cluster size. I then asked for descriptive statistics, and I had some difficulty with this. I had to hit preserve multiple times for it to work. I missed the P there. And then it would yell at me that it didn't need it multiple times, but then I'd take it out and it said it needed it again. So just, comment out the preserve if it doesn't work. I couldn't figure out the pattern to the errors, but I made it work eventually. So we'll look at school level summaries and correlations, and then we're going to get the, then we're going to save that information for calculations below. So here are the descriptives. So there are 94 schools, and on average, there's 139 students within them. So that's a number that we're going to use to compute things later on. The test scores range at level 2 from a minimum of about 29 to 61. So that's indicative of us needing random intercept variance across schools, school mean differences in math. In terms of the proportions, it looks like 70% of the kids on average here at the school level get paid lunch, 11% get reduced, and 19% get free. So in terms of centering the variables below, I'm going to recreate this in terms of school composition, these three numbers right here. A new thing that I've added here is to preserve the mean for school size, that 139. I am saving that as a variable so that I can include that in computations below, the same process in R. Then we're going to generate centered cluster means. So I'm centering the version that is paid versus free lunch at 0.3, because that is these two combined in terms of the proportion of students that get either reduced or free lunch. And then I'm centering the other one at 0.19 because that is the mean of that variable. So when all is said and done, we're creating a reference combination like this in terms of the proportion of students at a given school. This will be relevant in building pictures to show predictions at the school level to make sure that we have an adequate range of what's possible in terms of the distribution of this variable. I'm then doing within cluster centering, even though these are binary variables, because I will need that for my random slopes, and doing the same thing so that I can look at correlations at level 1 from math. And then I got all of the descriptives below, and then I'm saving the variances of those level 1 predictors for use in computations later as well. So here's the correlations. At level 2, by the way, the correlation between school mean math and the proportion of students who get either reduced or free lunch is negative 0.78. So the more poor kids in your school, the lower your average math scores. Now, I did not include the other version of the variable in this table. Here's why. We look at the ones and zeros. If I just put in this variable all by itself into a correlation matrix, it still means what I think it does. It's the zero group versus the ones. So this is the impact of having any kind of lunch discount. If I put in this column and I want it to represent the difference between reduced and free, in a correlation matrix by itself, it doesn't. Only when these two are predictors in the same model working together to delineate the group differences do they carry the interpretations that we want to have. In that case, this picks up just paid versus reduced, and this would pick up reduced versus free. But standing alone, that's not what this variable means. So I did not include it in the correlation matrix for that reason. And anytime that you have a dummy coding system like this, you would want to be careful not to do that as well. There are other kinds of contrasts I probably could have made, but I don't think it would make as much sense, especially when you get to the point where you're within cluster centering. So here's the correlations. Do you think math and free lunch status are related to each other?
Should they?
In a perfect world, no. But in reality, even in a
Yes.
Midwestern rectangular state that's fairly homogeneous in every other respect, yeah, unfortunately. So if I just ran a correlation in the student level data between student math scores and a binary variable for whether they get a lunch discount, essentially that's what this means, that correlation is negative 0.35. Now I can put that in a paper. Do I want to? Readers might want to see it.
But isn't that a smush?
Yeah, it's a smush correlation.
Yay!
Yeah.
Right.
This is the level 1 correlation amongst the within cluster versions of these variables, including the outcome. So within cluster math is functionally the level 1 residual variance when it becomes an outcome. That's what this variability represents. It's only correlated negative 0.23. At the cluster mean level, we get a correlation of negative 0.87. This is in the student level data set, so it's a different correlation than what we had in the school level data because of the differences in school size. This is the right answer because it's based on every school gets one data point. Yeah. So it looks like there's a negative relationship, the size of which is somewhat difficult to ascertain. But this smush correlation is in between the level 1 and level 2, as we would expect. That's my point. Okay, how are we doing so far? R, folks. I think everyone in here uses R, is that right? Are the Stata folks all home today?
I think so.
Okay, well then R, folks, you get your way.
We win.
Yeah, you win. So it did all the same things, read in the data, filter it to make sure that everybody has math and lunch, descriptive statistics, doing the sequential coding in terms of building my new 0 and 1 variables, building my new lunch indicator variables so that I can get the same descriptive information. The add unit means function is going to add cluster means for all the variables listed here, and I have named them with CM and an underscore in front today. At this point, if I had no underscore, it becomes like letter salad, like CMPVRF, so I just had to do the underscores. I don't normally do underscores, but I make exceptions when it's needed. So then we have building example for means as a level 2 data set explicitly, so we can run descriptives on that. Centering the cluster means so that 0 means something. So now our average school with respect to lunch composition is 70% free, 11% reduced, and 19% paid. All right, there. So that's the setup. I think most of this looks familiar. As you look through this code, is there anything that you want to ask about?
Just one.
Yeah.
So, with the add unit means function, can you do, or should you do a level 2 and a level 3 at the same time?
The answer is no.
That's what I thought.
Yes.
I don't have it set up that way, I just wanna make sure I had it set up correctly, thank you.
Yep, so the right way to do it, so that if you have a 3-level model with, you want to create 3 uncorrelated predictors, you take the level 1 units and you come up with the mean at level 2, and then you collapse across level 2 and level 1 and come up with the mean at level 3. Then they'll be uncorrelated. So that will require 2 steps, though. Yep. And you can always stick them in a correlation matrix to make sure that it worked.
Okay. That might be something I did incorrectly. We'll find out.
I did it, what I used to do is do the level 2 mean of level 1 and then the level 3 mean of the level 2 means. And then I found out that that doesn't work.
Oh, I didn't do that.
Okay,
I don't
that
know.
was my mistake instead.
I don't know.
It seemed logical to me, but it doesn't work because of the differential weighting. So
Yeah,
only if all the level 2 units are of the same size.
yeah.
Okay.
All right, thank you.
All right. Empty model? We start there?
Empty model for empty head. Mhm.
Empty model for a Tuesday in the middle of an overwhelming semester. That's where we are. Plus, it's good to review the stuff that you've already seen and feel good that you know what this is. So this is step 1. In longitudinal data, some folks might skip this, but in cluster data, this is a thing. People usually want you to at least provide evidence that you have clustering that you need to worry about. So this is something that you would want to report from. Nothing new here in terms of the code or the setup. Intraclass correlation is 0.15. Yeah, it is more than 0. So give me 2 different definitions of intraclass correlation. Who's feeling brave?
I can give one.
You can do one? You can
The percentage of variation that is at level 2?
Yeah, I would say proportion if you want to, in the
Proportion,
metric of this. This is ICC 1. Yep. So proportion of variance, that's at level 2. That's 1.
The correlation, the correlation between individuals in the same cluster on their response to an item.
Yep. So average expected correlation, people from the same cluster. Yep. How much of the outcome is due to cluster mean differences? Would also take that one. This is an effect size for how much dependency we have due to schools in our data, due to constant school mean differences. So there's several different ways you can talk about it. Pick one that makes the most sense to you. Is 0.15 greater than 0? Decidedly, yeah. So here's our likelihood ratio test. What this does is fit a model without the random intercept variance and see what the difference in -2 log likelihood would have been. So this is done for you in Stata for empty models. We have to do it ourselves in R with Renova, and here's another way of writing that. So yes, decidedly 0.15 greater than 0, we got clustering.
Outside of class, could we discuss a way to do this when you're using binomials? Because Renova does not work with binomials.
You may have to just write it out yourself.
Okay.
I will show you what that looks like in just a second, because I had to do that for the ordinal model.
Oh, okay. Well, very well. I didn't want to take up fast time.
Nope, and I expected someone would need to do this, so I built it in. Yeah. So we can use these results to compute a number of other quantities of interest besides ICC1. One is design effect. What's a design effect, folks?
I'll let somebody else answer though first.
Yes. Who hasn't talked yet? Who's feeling brave?
Anybody behind me?
You're smiling at me. He's feeling brave. He's not feeling brave. You want to phone a friend? Okay, he phoned you. Are you feeling brave? Not really. Okay, phone a friend. No design effect? You don't want to explain it? I would take the less polite version as an explanation. I have a way of explaining it that I think is intuitive, but maybe not the most professional way to say it. Erica, what am I thinking of?
But how much you're messed up into dependency?
Let's go with that one. My original text is how screwed you are from your clustering in terms of your power, but how messed up you are is slightly nicer. Mhm. Yep.
So basically, aren't you just finding out what the true size that you're working with when you're trying to find power?
That's what we're using it for. So
Yes.
design effect is the denominator that creates effective sample size. So we started out with 13,082 kids. But really, because of the intra-class correlation of 0.15, and because of the large number of kids per cluster, we don't have 13,000 unique pieces of information. We have a lot less than that. So the design effect is actually 22, meaning that instead of having the power for 13,000 students, we have the power for 595. So that's quite a difference. It's quite a difference. So in sample size planning with clustered samples, you want to work backwards. Let's say that you did a power analysis and it said you need 600 people. If this is the design you're trying to power, you need to go get yourself 13,000 people instead. Bummers. So the worst a design effect can be is 1, and that would only happen when there's 1 person per cluster or the ICC is exactly 0. And a design effect of 1 means there's no penalty factor that you have all 13,000 people in terms of unique information.
ICC is 0 means you don't need the other.
That's right. Only when this is exactly 0 would the design effect go to 1. However, is it going to stay 0? Anytime you add a level 1 predictor that explains level 1 residual variance for people, what happens at level 2? It necessarily increases. They're tied together. So your ICC may start at 0, but it may not stay that way as you start building your model. Question?
Oh,
No?
that
Okay.
was, I was pointing out.
Pointing up. Oh, yes, answering the question.
Answering the
There you
question.
go. Very good. So yes, we definitely don't want to ignore clustering. This is going to have a large impact on our conclusions. ICC2, though, as you might imagine, with a decent size intra-class correlation and an average cluster size of 139, intercept is quite highly reliable. So 0.96. I would have a good deal of faith in using school mean math scores to do stuff with. That's what I would interpret that. 95% random effect confidence interval is another thing we can compute. So this is, in general, for a random effect CI, the fixed effect plus or minus whatever z value goes with your level of confidence. So if you're not using denominator degrees of freedom, it's just 1.96 for 95%. And then the square root of the variance that goes with it. So this part is roughly plus or minus 2 standard deviations, given the random effect. So in our example, we would say that this indicates about 95% of our schools have mean math somewhere between about 35 and 61.
Where did you acquire the 47.756? I'm feeling silly.
That is my fixed intercept.
From, oh,
Right there.
Okay, yeah. 'cause my
Yeah, I
math
skipped
brain-
over it.
My math brain was thinking that's almost half of 95.
Yep. Nope, that's my fixed effect.
Okay,
It's
thank
the
you.
center. Yep. Yep. So in the handout that I gave 2 years ago, I was like, here you go. Here's some numbers. And now I had to go back and make them show up in things. So since nobody's here from Stata, here's your results, saving the numbers, using the saved numbers to compute these things. In R, same process, slightly different code here. So I'm asking for the saved variance components from the model as a data frame because then I know how to get to them. I'm sure there's other ways, but this is the only one that has worked for me consistently. So then I have school variance of 45. I have level 1 people variance of 253. Those are the same numbers that are up here in your output. So just accessing where they've been stored so I can do math on them. So then I computed ICC2, and I did do this instead as an addition. So I don't have to hard code 139. I can use this little function to grab the mean of the variable from the school level 2 data set. So that's nice. And then I did the same sort of thing to compute the random intercept confidence interval. I have the, let's see here. Is that right? That's not right. This is supposed to be, oh, nope, this is Stata code, that's why. And I just remembered why I don't intermingle the two. Because the colors are not enough. This is Stata code, this is our code. That's where we're coming at. So, my bad. I should move that out of the way. That should go up here. There we go.
So, question,
Mm-hmm.
on your third as data frame,
Yes.
okay, I don't know how else to describe that.
Yeah, that works.
So are you finding the average of your averages there? Yes?
This is in the school level 2 data set.
Okay.
The average of the column that is called N per school ID that was computed using the add unit means
So
process.
that's a weighted average based upon how many schools or whatever. Yeah, got it.
It's not a weighted average, it's a school level data set where each row is a school.
Oh,
And then it's a saved variable as to how many kids are in the school. And this is the mean of that saved column.
so they just average your school size.
Yes.
Gotcha.
Yeah,
Okay.
so rather than typing in 139 and having to
Well,
change it
well,
every
I
time,
know you
yeah,
said,
that was
but
the intent.
My brain is trying to process the picture.
Gotcha, no problem.
Thank you.
Yep, okay. So this part can be a little bit tedious. The hardest thing is just trying to figure out where the stuff is sometimes that you want. But asking for things to be printed is usually helpful, at least for me to be able to visualize exactly where things should be going. So, now what if you have an ordinal predictor?
Well, in your situation.
Yeah, so this is treating school lunch as an ordinal outcome for the purposes of computing its intraclass correlation. So this is a cumulative logit model instead. Last time we saw a binary one, now this is upping the ante a little bit. So it's MEO logit in Stata as a command, but since they're not here, skip that. And it is in a package called ordinal, a function called CLMM, cumulative logit mixed model. So all you need to tell it is what your link is. We're in logits rather than probits. It insists that lunch as an outcome is a factor variable. It wasn't in my data set, so I turned it into one temporarily. And then you end up with an estimated random intercept variance only in your model for the variance, because at level 1, it's 3.29, because we're in logits. So using 3.29 as level 1, you can still use the same ICC function, and its intraclass correlation for lunch is 0.35. So even bigger. So 35% of the variance in lunch status depends on what school you go to. Yes, indeed. And if we look up at the range and just descriptives in the data for a second. The proportions in this data set range from 0 to 0.8. So there are some schools where no kids get free lunch or reduced lunch, and there are schools where 80% do. Quite a variety. So there's a signal there in terms of school differences we're going to need to watch for. Now to your question, to do the likelihood ratio test, RENOVA wouldn't work, ANOVA wouldn't work, and so I was like, screw it, I'm just going to do it myself. So I had to fit the reduced model, which is CLM without the second M, because that is a single level ordinal regression. So this is what I used in the generalized class. And then compute the likelihood ratio test myself. So I have the -2 times the log likelihood extracted from this single lunch model, minus that from the empty lunch model that had the random intercept. And so then I get, that's my test statistic for a model that has 2 parameters, and the p-value is 0 to many, many decimal places. So this is what you'll have to do, is just manually fit the nested model and write it out.
Okay, that makes me feel better.
Yeah, I couldn't come up with anything else.
I
Vladimir?
found something that was like called Aphex or something that I was trying to work with. I'm not saying that you need to know. I'm just saying
Yeah.
I found something, but I couldn't get anything out of it that also balked at me. It wasn't supposed to work. So,
I don't know. Erica or Vladimir, do you know of a better way to do this than brute force?
I think that I use Gelmer.
GLMR? Yeah, Glimmer, as I would call it.
Exactly.
Do they have an ordinal model in it?
I think so,
Okay.
but I don't remember. Maybe I'm mixing.
I feel like I wouldn't have went to a different package if it did, but that could just be a false memory. So when in doubt, just make it work it out. That's what I would say. All right, so then I'm adding in my level 1 predictor for whether or not the student has a lunch discount, essentially. So this is paid versus reduced or free as the binary variable. So that's a fixed effect only in both of our models here, predicting math scores. Here's what happens. This is an easier one. 50.6 is the expected math score for what kind of person? It's not in logits because math is normal. Math is our standard normal.
Oh, sorry,
Yes, the logits were predicting lunch as an outcome to get its interclass correlation.
oh, okay.
Yes, so that's a separate model.
Yeah, okay.
Yes, that tells me I need to take a drink and slow the heck down. Water this time. Although, still enjoying my new tropical 7-Up. Did I tell this class about that? Okay, they're like, yes, we've heard. I teach 2 classes from the same chair back to back. I don't remember who I've told what. At least this year it's easier because there's fewer people in both, or you're sitting in different places when you are in both. There was one semester a couple of years ago where it was like 2/3 of the classes were the same people, and I got really like overwhelmed as to like what am I talking about now? And it was just too much. So anywho, yes, this is not an ordinal outcome. This is math as a plausibly continuous outcome.
50.6 is a score,
Yeah.
is whatever that means.
Yep, on the math test, what kind of student got 50.6? That's my question to y'all. This variable is coded such that paid lunch is 0
The person,
and some kind of discount is 1.
a person with, that does not get a reduced form of pricing on their lunch.
Yep, someone who pays for lunch has an expected math score of 50.6. What if I don't pay for lunch and I get a discount? What happens to my math? By like 9 points.
That's a lot.
That's a lot. On a scale of like 0 to 80 or something, that's a lot. In what kind of school?
Homogeneous school of nobody on free and reduced?
Do you see school anything in here?
Oh, wait, yeah, no.
For meh kind of school. School doesn't matter.
I don't care about school.
We don't care about schools, except schools are 15% of the variance, so maybe we should. In other words, what have I done? Yeah, this is a conflated effect. I'm either saying that both the within school slope is -9 and the between school slope is -9, or alternatively, I'm saying that what school you go to doesn't matter after you control for your lunch status. No contextual effect. Okay. So I asked a question in a formative assessment a couple weeks ago, how would you know in practice that this happened?
If your ICC is over 0.
Well, you know that it could happen if your
It
ICC
did
for the
happen.
predictor. But how do you know that a smushed effect has happened? One of the signs is going to be changes in the model variances. So I added Stata code to compute pseudo R-squares as well. That's using the saved results out of the empty model and then what the current results are from the saved current model. So that is, for instance, right here. This is saving the results to that table.
But that was the model that you used with villages, that's why you have your exponentials in that.
This one? Yeah, I lost it. Anyway,
No,
it's
but
in the
I think
output somewhere.
I saw your e to a power, I'm like, okay, you used your logis from, yeah.
Yeah, in Stata it saves variances as log standard deviations. Because. So here's my R-squares. So what is pseudo R-square? Here, I'll do a little review. If you had to explain it to somebody, how would you explain it? What's pseudo R-square for?
Additional, or it tells you basically how much better your model did at explaining or attributing variance compared to like an empty model.
Close. Attributing sounds a little bit different. What differentiates this from just like a total R-square in standard linear regression?
Well, total R squared is just how much, the way I think of it is how much variance your model explained.
Total R-square is how much variance did my model fixed effects explain, period. Pseudo R-square is, then, Not exactly. If total R square is what I would call a general effect size, because it's like how much variance in math did you get generally? The opposite of general would be specific. Like that's a question in your homework, specific. So total R square is one answer for an R square from the fixed effects. Pseudo R square is as many answers as you have piles of variance. It's per variance component, and in this case it is relative to the MD model. So what I have here is base. By the way, I fixed this too. So my function names are now base model and alt model. That way when I have model 2, it's not confusing. So alt model is the name of the argument. The model name in terms of the code that I just ran would go in there as what it wants to do. So try to separate those to make it less confusing. But 45 was all the variance across schools in math mean scores. That's what we got from our empty model. 253 is all the variance across students in math scores. We know this is 15%, we know this is 85%, just rounding here. In the new model, the level 1 variance was reduced by about 5% relative to what it was. So 5% of all the reasons why students differ in math has to do with their economic status. However, finger, that's the left hand, 40% of my random intercept variance was explained by student financial status. It's a lot. It's also impossible. The correct interpretation is not that student free and reduced lunch explains school math. This is the Trojan horse problem. It's that the hidden school variance in lunch explained the school variance in math. It's the level 2 part that's doing the work. But under this model, it's only actually doing part of the work, because this one slope says this is what the level 2 slope should be and what the level 1 slope should be. They're smushed. So wrapping this together, if you put in a level 1 predictor without a corresponding level 2 anything, and that level 1 predictor explains level 2 variance, it's a smushed effect. So we fix it. This is cluster mean paid versus reduced free lunch. Trust me, it's better than PVR with a bar over it, .j or whatever. Like, it's a lot of letters, but it's easier to read. Minus 0.3. Now, why 0.3? We talked about this a bit ago.
That was the sum from above your 0.11 and your 0.19.
Yep, 30% of my sample gets some kind of discount. So I'm setting it up so that my reference school has 30% students who get discounted lunch. And it is 0.3 because the school mean of a binary variable ranges between 0 and 1. So it's a proportion. That's why it's 0.3 and not 30, for instance. Now this version of the model has all of the original variation in my level 1 predictor, adding to it level 2 mean variation. So what this is setting up is what I call a within contextual parameterization. The level 1 slope is going to become the within slope. The level 2 slope is then the extra contribution of the school mean. That is the contextual slope. And so if you want the between slope, we would add the two together, and in notation, that's what it would look like. So we'll do that as a linear combination per usual. So adding that new predictor in as a main effect only, what do you think it's going to do? Explain level 2 variance or level 1 variance? Adding in this. Level 2, got 1 vote for level 2, 2 votes, 3 votes? Unanimous? Level 2. More generally, here's the rule, folks. If you write out the equations in this hierarchical way, any new effect that you add as a fixed effect explains the variance that's in its row. So if I add in cluster mean whatever to my level 2 predictor of the intercept, it has to explain random intercept variance. If I add in level 1 whatever to my level 1 model, it has to explain E-variance. So equations can be difficult to write at first, but I do think they're instructive for understanding the role of each new fixed effect in terms of what it's doing,
If you write it correctly.
if you write them correctly. But don't worry, folks. I expect you to make a reasonable effort and to be responsive to my feedback in writing equations. I don't expect perfection. And honestly, in your talks, if you have a very complex model that would make an equation difficult to write, it's going to be difficult for us to process. And you got to pick another way to explain it. In your job talks, do not write out a 3-level model equation and stick it on a slide in 10-point font. It's not going to go well. And yes, I've seen this. At the conference that I'm going to next week in 2019, I wasn't in charge of anything for the first time in several years, so I made a bingo card for the conference. It was a lot of fun. The center square was, can everyone hear me? We had bingo by the second morning of the conference, of those who were playing. So I think I'm going to do that again this year. But one of the columns of the bingo card, so there's places online you can do this for free. Like you can make up a bingo card and fill out extra answers and it will randomize it and you can send people the QR code and stuff. It's next time you're at a boring conference, it's a fun thing to do. But I had a whole column for poor choices of visual design. Like 8-point font on a slide, light green text on a white background, puts up a table from the manuscript as the slide, like those are boxes that I had. So if you want, for your presentations, I can share my SMEP bingo card with you and you can make sure that you don't cross out any of the squares. How's that? So I had a good time with it. It was fun. Not disrespectful at all, I swear. Anywho. Here's what happened. We know that the new level 2 school differences in lunch composition variable is going to explain level 2 school variance. So how does this change the story? If I'm a kid who gets a lunch discount, my score is still less by about 9. It's now 9.17. In the previous smushed model, it was 9.43. Yeah, it changed a little bit. And this is the point at which someone may reasonably say, who cares? It's like the same number. Why do I care?
Because you have something else that's something to explain things.
I have something else. This model ignores the possibility that composition matters. It says the between slope is negative 9.4 and so is the within. In the within contextual version that I've got here now, the within slope is close to -9 like it was before, but now this is the contextual effect. For every additional unit of school mean lunch, math is lower by almost 17 points. Now, school mean lunch, what the hell is that? If you write that in a paper, no one will follow you. What am I referring to in English? Exactly, the proportion of students in a school who get discounted lunch, we'll say at this point, free and reduced. That's what this variable means. Proportions range from what to what again? 0 to 1. So what is a unit change in terms of this slope? It's not, it's a proportion.
No, that's 100%.
Yeah, so 16 is the difference between a school with no poor kids and all poor kids.
So isn't this where you recommend that you divide it by 10?
Exactly.
So that you're saying it's per 10% in your write-up, not your model.
That's right. That is what I would do next because this is the full range of the variable and it's not even observed in the sample. Our sample goes from 0 to 0.8 on this variable. So I would move the decimal over like that and say for every 10% additional poor kids, my school's mean lunch goes down by 1.7. That's easier. And yes, I know poor kids is not the right term for this, but just, can you forgive me? There's too many damn words in here, right? low SES, economic disadvantage, resource lacking, like pick a nicer term. Poor kids is what I'm going with today. This is too much as it is. So if you're like, yeah, okay, I can move the decimal over, but is there a way that I can be lazier about it? Yes, there is. So I showed, I think, is it this one? I think it's down the road. I wrote out Lincoms and contest 1D statements to actually move the decimal over, to divide my coefficients by 10. That way you can like fix a whole table at the same time if you want to. But yes, per 10% is an easier way to do this. So said differently, the previous model assumed no contextual effect. This model assumes a large one. So what is the between slope actually supposed to be according to this model? How do we figure it out? This is contextual. Add them up, up. Yep. So within plus contextual is between. So if you want to get to the full impact of school composition, it would be like minus 25 or something. Yeah.
But yeah.
It would be here. Minus 26 and some change. So I'm doing some other stuff here. So far we've learned about total R square, pseudo R square, and what if you just want like an effect size for a slope, like a Cohen's d or a partial R? I made a function for that. 2 times d divided by square root of degrees of freedom, I think, if memory serves. I wrote it down here somewhere.
Yes.
Yep, that's what it is. So that's the stata code to do it. In R, I made a new function. There's like 6 or 7 new functions in this example, by the way. I went a little crazy. This one is called fixed effect sizes MLM. And what it does is take this table, remove degrees of freedom, remove t, and then use those to compute 2 no columns at the end for Cohen's d and partial R. So this table is something that would be suitable for reporting in a manuscript. Estimate standard error and p-value at a minimum, or stars for your p's if you want, and then one or both of these effect sizes. Now these don't make any sense for the intercept. You can remove those. But d's are in standardized mean difference units. R's are in some kind of correlation unit. Take your pick, I don't care. So this is yet a third option in terms of how you can report effect sizes per slope if you want something that's more specific. And I added a function to do that to contest 1D statements as well. So contest 1D we've seen, right? These do linear combinations. So what am I doing with this little piece of code right here? This is the results of our previous model, and it's 3 fixed effects. Adding 2 things together, yeah.
You're adding your 2 non-intercept slopes.
Yep, adding my 2 slopes. So I am building a between effect within plus contextual. That's what I'm doing. So then it spits out my minus 26, standard error and p-value, and I added, the function then adds these values to that. I will note that this value differed, these values differed from Stata, and so I had to do a little digging. And it turns out that Stata decided that the degrees of freedom were 86, and R decided that they were 79. So slight differences across
Now,
packages.
do they both use the Saturn?
They both use Satterthwaite, yeah, but it has to do with who programmed it.
Awesome.
Yeah, it's super great. So this is yet another reason why I usually recommend that you write exactly what package, what function, and what version, so that anyone could figure out like why your numbers might be different if they're not backwards compatible with something else. Yep, it happens. Okay, so which of my 2 variance components should have been reduced, did we say again? By our new contextual effect? Level 2 or level 1 or both? Yeah, which variance component should be reduced by adding in this new negative 16 slope? This is school means something. Level 2. Yep, so here are the changes in R square. So we used to have 40% of the random intercept variance from a smushed effect. It went up by 30%. So now we're up to almost 70%. At level 1, we were at 5% before. It's basically the same, a tiny little difference because that within effect changed a tiny little bit. But this right here is my contextual effect. It is the extra contribution of the school mean above and beyond the effect of the level 1 variable. In total, the between school effect is the 0.69, that's the effect size for it. So if I were reporting this out, I would say that 70% of the 15% of school mean math differences is due to school lunch composition, whereas 5% of the student differences in math is due to student lunch composition. All right, how are we doing? I'm trying, we're trying. And at this point, I was like, I know they're going to be overwhelmed, I'm going to help. So I yellowed everything that's new. Now, random slopes, that's what Unit 4 is about, right? Conceptually, what's a random slope? I'll take gestures. This is a random slope.
It changes just based upon your other additional factors.
More specific.
It changes because of your level 2.
What's it?
Your slope change,
Which slope? We got 2.
all slopes.
Yeah, lots of words here. So just conceptually, you can pull up a picture. Random slopes. What's the difference between the picture on the left and the picture on the right?
The left is parallel, right is not.
Yeah, so this is the idea that within each of these clusters, the slope of a level 1 person predictor differs across these clusters, not just the intercept where they are. So the left picture is consistent with a random intercept only across these differently colored groups of circles. The right picture is consistent with a random intercept and slope model. So this would mean that the extent to which it sucks being poor can differ across schools. That's my level 2 random slope of my level 1 predictor. However, my level 1 predictor is the original version. If I were to add a random slope to it, I would create a smushed random slope in the same way that I had a smushed fixed slope at first. We solved that problem by adding in a main effect of school lunch composition. I can't solve that problem the same way on the random side. A random effect of a level 2 predictor at level 2 is not something that is easily estimable or interpretable. So we're not going to do that. We're going to do what is known as a hybrid specification, in which the interpretation differs across the 2 sides of the model. I know. Here's my original 0,1 variable. It still has a fixed effect. Separately, I am adding in a different version of that level 1 predictor that has been cluster mean centered. And I am giving it only a random slope. So in the code, for instance, let me get down to the R code. I have the original PVRF in the fixed part and the within cluster version in the random part. I am doing it this way so that my fixed effects stay within contextual and my random slope stays within regardless because I set it up using cluster mean centering. So this sounds crazy, but it's not. And you should have no problems in estimating this. If this makes your head hurt, here's a way to solve it. Make them match. Then your fixed effects are within between, and your random slope is still unsmushed. But if you're in a context in which you want contextual effects, then doing it this way is acceptable. Survey says, here's our new variance. It's 14. Seems like a lot. We've also added a covariance with the random intercept, registered as a correlation here of negative 0.5. How do I know if we need this new random slope? Likelihood ratio test, our friend Renova. Survey says, yep. Okay, I need a random slope. Slope variance is 14. Now what? We can do some things to help understand what that means. So first thing I want to point out, the fixed slope has changed. It was minus 9.17. It is now minus 8.4. It means something a little different. This is the average slope across the school slopes, whereas this over here is just the slope, period. Weighted versus unweighted. Likewise, look at the standard error on this bad boy, 0.33. After adding in a random slope, 0.58, almost double. So this is the problem that statisticians warn about when people say, do I have to test random slopes for everything? They would say, yeah, because even if you don't want them or care about them, your inference about the fixed slope depends on having the random side to go with it if it's needed there. In practice, however, if you add a random slope for everything, you're going to break your model. Even in Bayes. Bayes can only fix it up to a point. So we can do the same kinds of things we did with the random intercept to try to break this apart and make it a little more interpretable. And this will be a great place to stop for today, I think. But yes. I don't ever look at that clock because it's weird. It sometimes skips like 2 things at once, or just it gets off. Yeah, I know. It's crazy. So random slope confidence interval. Same idea as random intercept, different ingredients. The middle is still the fixed whatever. Before it was the fixed intercept, now it's the fixed level 1 predictor slope. The variance that goes in here is not the random intercept variance, it's the random slope variance. But otherwise the process is the same. So minus 15 to 1, minus 1. That's the number of points that 2 kids from the same school would differ by if one of them has discounted lunch and the other pays. On average, it's a deficit of about 8.5 points, but that could be anywhere from minus 15, in which, oh crap, that's really bad, to minus 1. So this is a real life consequence kind of result. Like a random slope is a really esoteric thing, but if you think about what this means from like an equity perspective, it means there's a lot of differences in how equitably the students do who are poor in their math scores. Some places it makes a bigger difference.
Making sure I'm understanding this correctly.
Mhm.
So the negative 16 to negative 1.
Yep.
That's the 95% confident interval range for the slopes that are generated within the schools.
Yeah, so essentially like if you put, let me go back to the equation. If you put these 2 things together into one variable, right, the school's slope, that slope ranges between negative 15 and negative 1 in the sample.
Okay.
Assuming symmetric distributions and normal and you know, all the things, right? This is like a hypothetical result. Yeah.
Perfect world.
Yeah. Yep. So I would find words to describe these sorts of level 1 effects so that your reader doesn't get completely overwhelmed. Like gap is one. So like in Vladimir's project, he talks about the gender gap. This could be the lunch gap or something, if you can come up with a word for that. Size of the deficit, something along those lines would work as well. We can also do random slope reliability in the same way that we did random intercept reliability. So it's the slope variance that we just found, divided by that plus the level 1 residual variance, divided by cluster size, times the variance of the predictor, the slope is 4. So feeding all that information in here gives me a slope reliability of 0.58. So not super high. However, not that unexpected given this variable has very little variance to it. So then here's some code that does the things. And I'm also saving now my new model as a new baseline. So doing pseudo R square moving forward, this is my new baseline. Because this has 3 different piles in it, and I want to watch what happens to each of them. If I try to compare back to the empty model, it's going to get weird, because the empty model has residual variance and random slope variance mixed together as one thing. And because this intercept is unconditional, whereas in the random slope model, it's specific to this variable being 0. So it's at a particular point. So none of the variance components in the empty model have the same contents or interpretation as they do in this one. So to me, this is like a new starting point for building models further that would explain this new variance component, the random slope across schools. Okay. One last question. This is a school variance, right? Across schools? What kind of predictors are going to explain school variance? School things. That's right.
So that just means if it's like a 1 more whatever for the school value, yes?
A 1 more whatever?
1 more increase in like the percentage increase of favor dues.
We could do school composition, and indeed that is what's next.
Oh, sorry.
Yep, no, that's where we're going to head. Yep.
What was that one?
This is the size of the random slope variance. It is a school property. School predictors are going to explain it, but they're going to do so through cross-level interactions. With the predictor, the random slope is 4. So this is a reason why it's bad to be poor, and the extent to which that gap varies across schools. An interaction of school composition by this predictor can explain it. That's what's coming on Thursday, but not today.
This is all recorded.
It is recording, and the angry buffer message went away halfway through, so I'm optimistic that it's a decent recording. Optimism is what I can give you. Okay. All right, 1:45. Anything you want to ask about quickly before we adjourn? Nope. Okay. Let me know if you need anything. I'll be looking over your outlines and hope to get you feedback very soon. Otherwise, yeah, nothing's due next week, right? So I don't have to remind you to do anything. Breathe, sleep, and eat. Okay? Those are the things you all need to do. All right. See you Thursday. Thanks for being here.